We move from the geosphere to the last two reservoirs of the surface, the atmosphere and the oceans, or the liquid water. And let's start with the modern atmosphere. So the modern atmosphere, as you know, is contain what we consider two inert gases, nitrogen and argon. Argon is really inert gas, is one of the what we call the noble gases, with the helium, neon, and krypton, xenon. But the nitrogen nitrogen have so strong covalent bonds that is mostly behavior like an inert gas. And then you have two reactive gases, oxygen and CO2. And in fact, here I reported the concentration of oxygen corrected by the presence of CO2 that is increasing. So when we arrived here, it was 425 ppm. When I make my studies in geology, it was 380. And when Muriel born in the start of the Industrial Revolution, it was 270 or something like that. So we gain mostly 200 ppm in, or a little bit less in 300 years, 200 years. So this is the atmosphere, okay, to keep in mind. And we could define this an habitable atmosphere. So I personally define two possible ways. That is probably two different views. Maybe one is more a Lamarckian view and another Darwinian view. So what is precede what is, for me, it could be an atmosphere that has modified its chemical composition by interacting with an evolving biosphere. We will discuss about that when we speak about oxygenation of the planets. Or it could be an atmosphere that has evolving chemical composition to sustain life. So one helps to the life, or the life help the atmosphere. It's probably either one or the other, neither. But the two is reacting together. And we will see that the biggest change in the history of the Earth, the oxygenation, is probably a combination of different reservoirs interacting each other, what we call a perfect example of Earth system science. There are other types of atmosphere, so what we call the primary atmosphere, that is formed by the accretion of the gas that are in the protosolar nebula disk, that have a composition, a solar composition, so is a solar origin. And generally this kind of primary atmosphere are very thick compared to the secondary atmosphere, and they are mostly the atmosphere we found in the giant planets, compared to the one thin that we found in the rocky planets. They are what we call the secondary atmosphere, the form from volatile material that has been accumulated by the impact of planetary bodies. So you have only two types of planetary bodies, meteorites or comets, and we will see a little bit about that. And yesterday, Katrina made a very nice presentation about comets, so you already know. Frank, unfortunately, misses that. So we have one of the specialists of planetary atmosphere. He did with his PhD on that. So the primary atmosphere is very easy to recognize. Just you observe what is going on, for example, in Jupiter, and so you have the composition, and you understand why we say it's composition of solar type, because the two main gases is hydrogen and helium, so like the sun, and then you have other type of elements, and probably this trace now is very long because this is already old, 2015. Again, Encyclopedia Astrobiology, the project with Muriel, and this is Teresa Encrenard's data, and including the famous phosphine that is being claimed to be found in the clouds on Venus, that is possible, and that indicate life, a little bit to find life in these huge tropical cyclones in the middle of the Jupiter. So the Earth atmosphere have no what we call a solar origin atmosphere. It's not a primary atmosphere, and this is explained by this cartoon. I show this cartoon because if I show my cartoons, you will quit the rooms. I have one of my cartoons because I'm not good in drawing that. And what is going on is that the rocky planets have also this primary atmosphere, and then has been lost, is what we can see here. So the primary atmosphere is is arriving, and then you have this arrow that strip out the atmosphere, and then you have something that remain, that is hydrogen and the helium-3, the isotope 3 of helium. And then you have impact with the bodies, then bringing you the water, the CO2, the nitrogen, etc., etc., etc. So several about you know the story. And this is when the sun is very young, because the sun in the main sequence, like our sun, when they start their activity, they pass through what is called the T-Tauri stage, from the name of a constellation that is somewhere very close, I don't know, 3 or 4 parsec, I don't know, that is characterized by very strong stellar winds. So you have something like 10,000 or 15,000 stronger solar winds compared to the present flux of solar wind that is cleaning the actual solar system. And so this charged particle literally strip out this original atmosphere that is replaced later. But we have a witness of this, that is the helium-3, so the mass 3 of helium that is pure of solar composition. So if you go in the rocks and you go in the basalt, you are lucky to avoid atmospheric contamination. That is mostly impossible. You should find a ratio of helium-3 helium-4 that is the one of the solar wind, so 100 times the atmosphere. Until now has been found 60 times, because the Earth, you have everywhere present-day atmospheric contamination. But that is confirmed that inside our planet we still have some solar composition gas. Is the only one, maybe neon, but there is a long debate since 40 years. So the idea is that you have this famous hypothesis, the late Venir hypothesis. When I was student, the late Venir, I was coming very late in the history of the Earth, at 3.8, 3.9. There were people that were connecting the late Venir with this famous late heavy bombardment. Today there are people that ask themselves, is never even existed this later heavy bombardment that is based on dating of lunar rocks that probably came from the same crater. So they needed to have new lunar rocks to understand that there was this pulse. But today we think that it's the late Venir. So the late Venir is the addition of extra bodies, meteorites or comets from outside, bombarding the surface of the Earth and bringing down the future oceans, the future atmosphere. And this is probably happened very early. Some model, like the model of Morbidelli, is when the Earth was accreted at 70% of its mass, somebody a little bit later. But anyway, it's in the first stage of the planet formation you have this. The volatile is, they are partitioned into the magma oceans because they have high solubilities, and then the planet, the gas out and form this secondary atmosphere. So let's see, so this is resumed in this cartoon that I made, and so you will see the difference between a serious cartoon and my cartoons made by a dummy. So you have bodies here represent asteroids like Vesta asteroids, but it could be comets. In fact, it's a mixing of the two. But as I said, Catherine, yesterday, at least for water, you have very few, and also for atmosphere, except xenon, maybe krypton and argon. The amount of cometary contribution is very low. And then you partition this inside the planets, and then is the gas through volcanism with times. In reality, some people, well, there are several evidence that the gassing of the planets has been catastrophic at the start, and somebody connected this catastrophic the gas with the giant moon impact. But again, I'm reading and more reading about that after years, and I think that everything have to coincide with the giant moon impact. So maybe something up, it was, something not. But what is important is to understand what kind of secondary atmosphere is, what is the source of the gases, and the partition into magma, and especially the gas speciation that depend of the redox state of the mantle. And so it's coming out as a CH4, it's coming out CO2, so we have a reduced atmosphere, we have an oxidized atmosphere, everything change for your life kitchen. And so how you produce organics. I'm a geologist, so I go on the field as Jean-François, but here the field is far, but I could start to looking around me. So when I go on the field, I look around, I try to understand what is the meaning of this TTG, and so I give an hypothesis. So let's go on the other two telluric planets and look at the atmosphere. So you have here the atmosphere of Venus from the last, I think, the only mission gone very close to Venus. And so you have a CO2 dominant atmosphere with some 3-4% of nitrogen, and then you have sulfates or argon, a little bit of water, very small. The Venus is 400 100,000 times drier than the Earth, so the water is very little. And then you have Mars. You have, this is the data from Viking 1, in the parentheses Curiosity. There is a 30 years difference, but there are no differences mostly. Even Viking in 76, we were good to measure that because particularly we have the same number. Again, 95% of CO2 around and 2-3% of nitrogen, some argon and water, CO, etc., etc. What about the primitive or young Earth? So we can calculate roughly this. Is a geologist's calculation, of course. And so let's do some backstepping calculation. So it's very easy. Let's take off the oxygen. Oxygen is, the little story is the product of cyanobacteria, but the story is more complicated. I will just give you a flavor of that because I think there is every week some paper coming out of the oxygenation of the Earth. So I should need the next 3 days, but unfortunately there is no sufficient foie gras for the next 3 days. So let's take off the oxygen in the calculation because oxygen is typical gas produced by biological activity. In fact, who is working exoplanet in this room is searching methane or searching oxygen or other species that can indicate life activity. And then the second one is increasing the CO2 because today the CO2 is trapped into carbonates and the biomass, of course, the organics. So we have 350 million gigaton of carbonates on our planet in the soil. And this is an example. Yesterday you saw Jean-François bring some stromatolite, very small with, this is stromatolite, just is make 2 meters diameter. This is one of the first carbonate platform in South Africa in 2.5. I don't remember the place. Jean-François probably know this place. I remember better. Huh? Pass, it's called. Yeah, it was 20 years ago. Thank you, Jean-François. So if we so what happened with the times, we have a natural sequestration, CO2 sequestration. Today we want to make a CO2 sequestration to improve the climates. And one thing is to do is to precipitate CO2 as carbonate. The Earth do that since 4 million years or some billion years or something. So if you take all this amount of carbonates contain CO2, is here, and we put back in the atmosphere, we arrive to the same number. 95-97% of CO2, 2-3% of nitrogen, a little bit oxygen was very small, probably even 0.0001 ppm, etc., etc. You have the noble gas always there, including xenon, but we will not discuss about the xenon. The question is, for you that are try to understand how life developed, is it this oxided atmosphere, make of N2 and CO2, good for life? Theoretically not, because this we have the famous Stanley Miller experiment where he reduces gases, NH3, ammonia, methane, etc. And he heat up this, he make electric discharge, etc. You know very well the Stanley Miller experiment, and he produced this famous primordial soup that is sold now by Campbell. This is the present oxiding atmosphere, but even with the one I presented, is not the best theoretically to produce amino acid or other molecules. So the people claims that maybe the first atmosphere was like the one of Titan. So this is an artist's view of Titan's surface with hydrocarbons, rivers, etc. This is from data of Cassini-Huygens space mission. And the people went on Titan because Titan represents what we call a prebiotic world. You have all the ingredient, organic ingredient in the atmosphere, but of course you don't have life because having organics do not mean having life. Life is different stuff. And so the atmosphere is made, it contains also ammonia and the methane and the nitrogen. And you have, this is a profile of our atmosphere here with the nitrogen, oxygen, argon, and this is the atmosphere of Titan. And you have this, we call the Titan has layers where you contain a lot of organic particles, including this famous hydrogen cyanide. In fact, we speak about HCN type atmosphere, primitive atmosphere, where you have this kind of molecules that are very important because is at the base for producing amino acid and so DNA molecules. It contains also benzene, other radicals, etc. So it's very rich in organics. And practically this atmosphere, this age, is a little bit the equivalent of this famous primordial soup. And so why not we could have this? To understand which kind of, as I said before, type of atmosphere we have, as I said, we need to understand the source of this atmosphere and then the mantle redox condition. So let's start with the source. So which source bring this kind of component? It was including water, so I will speak a little bit about water, but then I will go back to the ocean for the pleasure of Muriel later. Here we have on the right a chondrite, and here we have a comet. So they contain a lot of water, some of them, a lot of organics, and volatile. So if we look just to the hydrogen, so that means to the water, the potential deliverers is of course the comets, chondrites, and recently has been proposed enstatite chondrites. So the enstatite chondrites, was believed they were very dry chondrites, poor in organics and in everything. They form close to the sun, probably in the Mercury orbit. At least this is the general idea. I don't know if I missed some paper, probably, because that it says something different, but is forming in the interior of the solar system, so in a very dry place, okay? If we look at the content, for example, the water masses of the Earth, this included the oceans, but includes also the water that is in the mantle. Of course, in the mantle is not liquid water, but is hydrated minerals, etc. We suspect that we have between 5 and 10 times the volume of the oceans in the mantle. So this gives us this band. This is the total volume of the Earth's water. And the enstatite chondrite should be drier and not having the capacity to cover the amount of the water. But the new data from the group of Nancy say differently. Well, we will see this later. And this is the ordinary chondrite. Now the Earth-like planets, we will see in 1 or 2 slides, is believed to form mostly by enstatite chondrites, parents, and maybe mixed some other with a little bit ordinary chondrites, maybe not. I will leave the specialists discuss about that, but basically is a mixing of enstatite chondrite, maybe with a little bit of chondrite. And we have carbonaceous chondrite later that arrive, this in the late Venier hypothesis. And so carbonaceous chondrites, like Marchinson, Allende, etc., it's, well, Allende is not so much, but because it's a CV, they contain relatively a lot of water, and the comets even more. And so they can easily cover the amount of water on the Earth just if you add a few percent of this projectile on the surface of the Earth. As I said, recently has been several work of Loretta Piani in the group of CRPG that they remeasure hydrogen in the meteorite, not water, because being a reduced rocks, it contain hydrogen, it not contain H2O, because the condition of formation is not able to produce oxided species, but hydrogen. If you recombine this hydrogen somewhere on the surface of the Earth, you could produce water. And this is the band covering the total amount of water in the Earth mantle and the Earth oceans. And our measurement is in violet. And she showed that even mixing, for example, here 70% enstatite chondrite, 25% of ordinary chondrite, and 5% of carbonaceous chondrite, what we expect should be probably the composition of the Earth plus this projectile arriving, impacting, giving organics maybe to the Earth, and waters and atmospheric volatiles or atmophile elements. You arrive to cover the need for the planets. I will not comment more. I will go back. I will use again, I update some of my figures again on that. We can start to exclude the comets. If you, for example, plot the isotopes of the hydrogen that represent the best fingerprint to know the origin of the water on the Earth. Catherine yesterday explain very well better than me. And if you plot against one of the volatiles that is nitrogen, the comets are here. This is comets coming from the Oort clouds. This is comets coming from the Kuiper belt, so the famous Jupiter family, like the 67P. And here is the solar composition. You could have a mixing that explains the composition of the Earth, just mixing this way solar and comets. But you know that in isotope plots, it's rare to have a straight line. You have a hyperbole, and the curvature of the hyperbole depend from the ratio of the two spaces. So about this ratio. And if you use the ratio that we believe is the ratio of solar and planetary, cometary nitrogen and hydrogen, the mixing curve are this one. So the Earth is not at all passing through the mixing between solar and cometary water and atmosphere elements, but is close to the composition of carbonaceous chondrite, and I add also the data of Loretta and the astatite chondrite that is a little bit far, but okay, we could explain for some physical processes incorporation and having the same composition of the Earth. Here is a report also Mars and Venus. They have two different completely behavior. Venus lost the water. As I said, is 400,000 times drier than the Earth. And when you lose water or any kind of volatile, you lose cinetically faster the light isotopes than the heavy one. So the D on H is increase of several order magnitude because you keep the heavy isotope preferentially than the light one. It's just a question of kinetics. And the Mars that increase both the heavy nitrogen and the deuterium because the atmosphere has been lost in the oceans probably by photolysis. So this is a remnant atmosphere on Mars, and so you fractionate both to high value containing more the heavy isotopes than the light one that escape more quickly from the gravitational field of the planet. So we can exclude already comets from a major player for atmophile elements. Let's go back to the chondrites. This is a very old, so probably who is doing chondrite will be scandalized, is a Urey diagram, but I like it. This diagram reports all the class of meteorites. Don't ask me what is LLH. I read it once on a book and completely forget. It's depending from the chemistry and others, but I know the carbonaceous chondrite are here. The enstatite are here. The Earth composition is here. So here you have oxide iron on silica ratio, and here you have metallic iron or reduced iron on sulfur on silica. So higher this ratio, more reduced condition, higher this ratio, more oxide condition in the formation of this family of planets that break up and then became meteorites or asteroids. And there were people like Schaeffer and Fegley, etc., that they eat up, they make a pyrolysis of enstatite chondrites and carbonaceous chondrite, and as expected by their chemistry, the kind of volatile you can extract by pyrolysis of enstatite chondrite is reduced species, methane, hydrogen, CO. In carbonaceous chondrite is CO2, water, etc. So you extract oxide volatile and reduced volatiles depending the impactor. As I said before, it's not only the source that is important, but this gas, so these meteorite and comets impact the surface, a lot of volatility is lost because you can imagine during impact. So you need more impactor than you believe to have something that remain on the Earth. And they impacted during probably the magma oceans. So part is partitioning the magma oceans, and then we rejected catastrophically, maybe with a moon giant impact or through intense volcanism. Is not important. What is important is to know the redox state of the mantle. So the redox state on the mantle for us geologists is calculate, so the fugacity of the oxygen here report against the temperature. The fugacity is depending also from the temperature. We calculated this on the basis of the ratio of reduced and oxide species of iron. And so we have equilibrium corresponding at different mineral assemblage that represent the redox state of the mantle. So since probably 3.8, based on measurement on rocks, we expect that the mantle is quite oxide and is following this green line, that is the phyalite magnetite quartz. So is this mineral equilibrium, if you want, here. And this indicated that the mantle is relatively oxide. So it's an euphemism compared to the atmosphere, but is more oxide. As I said before, diamonds is formed from oxide form of carbon and not from graphite. So the diamonds also testify of this oxygenation of the mantle. And through volcanism, the gas species that is expected that go back to the atmosphere is oxide one: CO2, water, sulfates, etc. But in the past, when the planet formed, we expected for some period it was much more reduced, and they followed this blue line that is the iron wustite equilibrium, that is indicating more reduced phase of the iron. So the mantle was much more reduced than today. And so here is a paper of Hortensi et al. On scientific reports, but there are other, and show what it should be the gas speciation if you are at the iron wustite or even lower, because there are several models that show that the mantle, when it's formed during the magma oceans, it could be even more reduced the iron wustite redox state. And today, or since 3.58 billion years, the FMQ, the phyalite magnetite quartz redox. And this is the water. Here you have hydrogen, the CO2, and the CO. And when you are in reduced the mantle state, you should degas reduce gases. And when you are more oxide, like today or during the Archean, you should release more oxided species like CO2, water, etc. in the atmosphere. So this is the variation log step from 0, that is iron wustite. So in this side is more reduced, this is more oxide, and the 4 corresponded to this FMQ equilibrium. So can we imagine that so I go back to the famous figures at the start of my presentation, I add another planets in between, it's always the Earth. Could we expect an uninhabitable planet? An atmosphere with a mantle more reduced, that are degassing more reduced species like methane, hydrogen, etc. So some kind of Titan-like planets that is your prebiotic kitchen. And then we move to the life factory with the water we described before, with a stable crust, even buoyant and hot, with some water, volcanism, and CO2 and 2, so Venus-like type atmosphere. We could. Other people, they put this model later with the apparition of organisms producing methane, or we could even forget this, because if, as we saw yesterday, comets, and we know carbonaceous chondrite can bring amino acid. Ryugo analysis show there are other organics. Comets contain a lot of organics. You don't need a prebiotic kitchen. You have the organics directly in this planet. Then you have to make them assembling and following Darwin to make life, because life is the famous NASA definition is an auto-assembled system that follow Darwinian evolution. And so this is the big question. There were a lot in 20 years ago about the paper of HEN type atmosphere. So if we pass through this Titan-like atmosphere or not, this is discussion. I don't put here again ages, because I don't like, because when geologists put age, the other things is the true. So is somewhere between 0 and some million or 100 million years after the formation of the Earth. Go back to this atmosphere. Let's forget the Titan. Maybe we have this prebiotic kitchen. You already prepared the soup. The first organisms start to eat the soup. Very good. We are to this early Earth with this Venus-like atmosphere, so a lot of CO2 and 2. Initially, as I said, probably we are speaking maybe of following a model of Zanle, 1,000 bar of 300 bars of CO2. We don't know if you extract all the CO2 is in the mantle, plus the one is in the carbonate, etc. I think you arrive to 200, 300 ppm. The nitrogen, we don't know. There were a very old paper, editorial on Science of Jim Casting, that he told that the nitrogen probably have all through the history more or less 1 bar, because being an inert gas. This has been taken as face value, because Jim, but is probably maybe have a reason, but we don't know in reality nitrogen, what is the amount. There is several papers. Some say it was only 0.2 bars, somebody say it was 3 bars, because nitrogen is not a greenhouse gases, but if you had the pressure of nitrogen in a greenhouse atmosphere, you increase the effect of the other greenhouse gas like methane or CO2, and so you increase this. So has been said a lot of things on nitrogen, and being a specialist on nitrogen, I will not speak about nitrogen, like I will not speak about xenon. Okay? And we saw before that, okay, maybe it was 1,000 bars or something, and one model is to have plate tectonics and take this CO2 back on the mantle, but I explained a few hours ago, fortunately when Jean-François was not there, that plate tectonics, as we know today, was not working at the time. It was something, it was tectonics, but it was not working, so it's much more difficult and long to recycle a massive Venus-like atmosphere with absence of modern plate tectonics. But at a certain point, the CO2 is decreased, and we have what Frank is a specialist, so I cannot say nothing about that. The Fante-Young-Sun paradox. We needed to keep CO2 and maybe CH4. I will speak about CO2, but today people mix CO2 and CH4. We needed to have greenhouse gases keep in the atmosphere for a long time through the geological era, because we have this problem. The stars of our generation, so like the sun, when they start their nuclear reaction, they are not at the maximum of their power. The luminosity, it keeps times to it increase during the life of the star. So when the planet form here, these are two different models. The luminosity of the planet, it was 70% of the present times. And I remember you that the biggest heat producer on this planet and energy is not the heat coming from the planet. The major number of watts for meter square on this planet is the energy we receive from the sun. So less luminosity, it means less energy, it means a colder world. But the planet was not cold. Here you have the age again, so origin of the planet is here, this is modern times, and here is what has been extrapolated of the temperature of the oceans, of the seawater. You have any kind of crazy numbers here, and mostly is based on stable isotopes measured in rocks of different age that we know they form in the marine setting, so is a marine sediments or rocks. And any kind of rocks, it react with the seawater and exchange is oxygen isotopes. Not the deuterium, because rocks contain mostly no hydrogen, so the deuterium is very conservative. This is the reason that today we can measure the DH of the modern oceans and we can compare directly with the one of comets or chondrites, because the oceans have little change reacting with the planets is composition of hydrogen, while the oxygen is exchanging between the rocks and the fluids, and the amount of mass fractionation is dependent from the temperature. And so if you keep constant the oxygen isotopic composition of the oceans, this is a mistake because the oceans probably change compared to the hydrogen reacting with the rocks in times, but let's say that is constant, and you measure oxygen insert, oxygen carbonates, or now they are doing the triple silicon or oxygen in a chert, so the oxygen in the silica and the silica isotopes. The amount of fractionation is temperature dependent. And so you can calculate at what temperature this isotopic exchange happen. And this is this curve that give you the temperature. We have any kind of value, but the people now believe more to these silicon isotopes. There is a very recent paper of the same group in Paris that used the triple silicon isotopic system. So 3 isotopes, more than 1 is always good if you control well your system, and arrived to the same conclusion, probably a 3.5, because we don't have except the acoustic gneiss, but it's not marine sediments yesterday, so it's the oldest sediments is 3.5. Probably we have oceans around 50 degrees. Today is 15, taking in the models average temperature. In Canada probably colder, but 15 let's say. And the cool down during the time. So you have a world that is with less energy from the sun, so you should have a colder climate, but with hotter oceans. And we have no glaciation this time. The first glaciation is the Uronian. So we have in the period of more modern times, planetary glaciation is what is called a snowball glaciation. The first one is the Uronian at 2. Here is report 2.5, I think the last paper I saw is 2.2, 2.3, 2.4. It's like the oxygenation is moving continuously. Again, on snowball you have probably not 1 paper per month, but 1 paper every 2 months, so it's continuous moving. That means that we have no trace of planetary glaciation, hot oceans. That means the planet was warm, and to keep a warm planet, you know today, you need a greenhouse gases in the atmosphere. And so probably you have this. As a geologist, again, we look at the rocks to try to know how much CO2 it was. This is the partial pressure of CO2. Okay, so is 1 bar here. And this is the solar luminosity. This is the age, so for 4.5 and 0. The first indication of the amount of CO2, I will explain how has been calculated this. It's around 2.7, 2.8. It's become more and more detailed, these geological records in recent times because we have much more rocks, of course. And these 2 curve is what we should have of CO2 in the atmosphere. This is a model from Jim Casting based only on CO2, but now people integrate also CH4 because it was probably present, I will show in a slide, all along the history of the Earth. In more higher amount than today, to keep the surface of the planet at 0 degree and 15 degrees. So there are 2 evolutionary curves calculating using just CO2 as greenhouse gases. And this value has been, except the star, has been calculating looking at the iron species that are in paleosols. I will show you what is a paleosols and what I'm speaking about. The star, if I remember well, there is 1 or 2 papers, I think also the group of Jim, that they look at the alteration of micrometeorites, I think, coming inside the Earth, and the alteration is different if you, or meteorites, old meteorites, or tektites, if I remember, and the alteration change depending on the composition of the atmosphere, and so they calculate indirectly what it was the amount of CO2. I cannot comment on that. I'm not special of that. But this is a paleosol. So this first part is few points, and then we have a nice paper that have go around on the world and looks hundreds of paleosols, and so is much more detailed. And this is based on a very old paper of 95 Rye and Holland that has been contested the model and with a new model from Sheldon in 2006 that is based on looking between silica containing iron and pure siderite, so is the carbonate of iron, in the paleosol. Paleosol is a lithified ancient weathering profile, is an old soil. The first one is around 2.7 in Pilbara Craton, so Western Australia. There are other in South Africa, a little bit more recent, I think, but Jean-François can correct me. And inside you have different species, and you have this reaction. This was the original reaction that has been worked by Rye and Holland. There are other reactions now using other species. This is a silicate of iron, is a clay containing, so is a hydrated silicate containing iron, granulite, and that can convert in siderite, but you can precipitate siderite with high pressure of CO2. So depending on the pressure of CO2, you can favor in one direction, on the other, the reaction. So you can have granulite or siderite if you have low pressure of passive pressure of CO2, or siderite higher pressure of CO2. Again, it's not the absolute true, because there are, from the geological point, several problems. The most interesting layer is the superficial one, when you react directly with the atmosphere, but we are speaking of 2.7 even lithified soils, and in 2.7 billion years, probably the upper part has been eroded, so the one that can give the best information has been lost, because you cannot stay on the surface of the Earth for 3 billion without losing part of the rocks. And there are other reactions that appeared, so it can be discutable, but it's a way from the geological point of view to have an idea how could be the CO2 in the atmosphere at that period. Of course, it's probably there are other models. It was a model with just taking account, if I well remember, methane. The Pavlov model is again a student from Jim Casting. And now the people use CO2, CH4, methane models for greenhouse, because we have both gases a long time with higher amounts than today. So this has come from the review of Kathleen and Zal in Scientific Advance in 2020 about the Archean atmosphere. Here you have the nitrogen, maybe lower than today, and reaching mostly the 1 bar atmosphere in recent times. Depending, this is all modeling depending, except a few work and few analysis has been done. I will not speak about that, even if I am specialist of the nitrogen and of the Archean, because again, we have people presenting models that say there was 0.4 bar, and the other people say that no, it was 3-4 bar, because as more you put the nitrogen, more the other greenhouse work better, because you increase the effect of the greenhouse gases adding pressure of nitrogen in the atmosphere. You have here the CO2 decreasing with times, and then you have the methane that decreases with time. We have a drop at 2.5 because we have oxygenation, and today why we don't have so much methane in the atmosphere, because methane survives 12 years in the average, and then is oxidized by a rich oxygen atmosphere, so the methane is converted in CO2 and disappear on the solid Earth, while at the times without oxygen it could have been in much more amounts than today, maybe sustained by the appearance of methanogens that in their metabolic activity they produce methane, like the cyanobacteria they produce as waste oxygen. And maybe going back and then going down again at the second pulse of oxygenation, and then you have much more detailed models. And then here the oxygenation. In the last part of this talk concerning the atmosphere, before moving briefly to the oceans, I will speak about oxygenation. You have 1,000 this curve. I take this because it's a paper they use machine learning to took all the data existing. I think that we don't really need the machine learning because still maybe we have a few thousand data, so we could do by hands, but why not? And so they try to put all together to have a better curve, but at the end I arrive to the same curve. The only things that I don't like this one is the go from right to left, because here's the planet formation is here at 0, while all the other that is generally presented is exactly opposite. You have here the formation. Sorry for that. I just want to change it. If not, Muriel say always the same diagram. But again, the Earth has been for half of its existence anoxic. The amount it was very, very low, maybe 10 to the minus 6 times the present atmospheric level, so the 20% volume that we have today. And then you have what we call the great oxygenation events. You go up to 10 to the minus 2 or something, 10 to the minus 1 is not so much compared to 20%, but is enormous in the history of the Earth. So you start to see appearing oxidized minerals and a lot of change. The ocean is changed, become more oxygenating, etc., etc. This is the boring billion that is not at all boring, following Galen Halvorson. Is a lot of things is happening. Is the Proterozoic. Eukaryota is appearing here. And then we have a second oxygenation in the end of Proterozoic, around 800 million, where we don't know so much about. There are few models, and I will not speak about, and still is very open question. In reality, this one is very open question, because we know this happened. We have trace in the geological record, but the complete mechanism remain very elusive. I cite Kettling and Zanl in 2020, and I agree perfectly with them. Here you see that you have a relationship between the change of oxygen and the changing of the organism living on these planets. Is another big question. You have a lot of papers. Oxygen favorizes the apparition of these species of kingdom, or it predates. So it's depending if you are thinking in a Lamarck way or a Darwinian way. I don't want to speak about that. I was thinking to put something about that, and then I saw that Donato Friday will speak about the biosphere and the geosphere evolution. So I will leave him. He's probably know much better than me. What is the real relationship between the apparition of, for example, mammals, superior animals, or eukaryota and the oxygen? My next project will be about oxygenation eukaryote in Proterozoic with Galen Halvorson, but I come like a neophyte, so I don't know so much. We have a lot of geological record for that. I choose this even if the story of this rock are more complicated than you can find in the books, but Jean-François brings several of them. This is the famous Bandera formation. This is a Canadian one, you can understand from the symbol. So this is kilometers of silica, iron poor silica, because still there is iron inside the chert. So this level of pure silica is not pure, there is iron, but much less than the level where you have mostly iron and few silica. This is important because before we always said there is pure silicon, pure iron. It's not true. There is iron everywhere, but more rich in someone. They formed mostly 90% at the same times, but you have a 3.8 issue of Bandera formation. You have Bandera formation at 800 millions, but this is related probably to a snowball episode. I will not speak about that. And is one record indicating the oxygen is start to accumulating in the atmosphere. But we have other records. We have uranium deposits, sulfates, sulfur in the atmosphere, etc. So we have a lot. But as a classic geologist that I was in another life, I just speaking briefly on the Bandera formation. So as I said, the Bandera formation is present everywhere, but are mostly concentrated with an enormous peak of production at 2.7 around and 2.5, let's say 2.7, 2.6. Amersley Basin, here the people you saw yesterday the map that Jean-François bring of Pilbara, West Australia, you see where is Hamersley Basin. There is the biggest pit of production of iron, because iron is extracted on this planet from this rock. This is the rocks giving iron to humans. And but as I said, we have a 3.8, but this is very episodic, very small local outcrops. The majority is coming here and is coming just before what we think is the Great Oxidation event. Again, the Great Oxidation event, when I was student, it was around 2.5. Now every month we move it, is 2.3, 3.2. There was a paper 2 weeks ago putting again 2.32, I think. But let's say 2.5 to 2.3, 2.2 is the Great Oxygenation event. So this predated the oxygenation event. And why? It's because the iron comes from the mantle, like all the metals on the Earth. And it was brought in the oceans. At the time, the oceans, it was acidic, not so much, probably pH 6, 5. It's depending what you use in the atmosphere if it is only CO2 or CS or methane, etc. You can calculate the pH at equilibrium with the atmosphere. Of course, there are other factors entering, but let's say 6. And it was without oxygen. So the time scale of the residence time scale of iron in this condition is 1 million years or more. That means that you have an Archean ocean that was extremely enriched in iron. Today, we have an alkaline ocean with a pH of 8.2. We have also PhD studying that. pH of 8.2, and we have oxygen. And so the time scale of residence time scale of iron is 1,000 years. In 1,000 years, precipitate like hydroxide of iron. Okay? And so the idea is that this oxygen starts to accumulate. It was predated by the iron that precipitate, and when it's finished to precipitate, it starts to accumulate. The story is more complicated. So in all books, you read always the little story that cyanobacteria arrive, make oxygenic photosynthesis. This is stromatolites. Stromatolites are not cyanobacteria, it's just bioconstruction that is favorized by the presence and the metabolic activity of cyanobacteria. So it's like a carbonate biofilm interlayered by detritus, grains of sands and others, and make this nice dome, like the one we saw in South Africa, or yesterday the sample brought by Jean-François. This is a modern one in Shark Bay in Australia. You have also in Bahamas some. And so the little story is that cyanobacteria start to populate the Earth and produce oxygen. Okay, nice. We have a stromatolite of 3.5 billion years. This is the famous Trenden locality. The one that I told some student has been excluded by the official map of Australia to avoid to have tourists going there to touch, because it's protect astrobiological sites. But of course, the other people said, okay, stromatolite is a morphology, so you don't need necessarily bacteria, that organisms that make the oxygenic photosynthesis. It could do anoxic photosynthesis or other metabolic pathway. So it's not really a proof that you have this. When we start to see about the carbon fixation, etc., we see and more papers that say that it was very old, probably before 3 billion years. So maybe the mechanism was already there. Other people say, okay, but we have this producing oxygen, and it start to produce oxygen well before the 2.5, 2.2, but we have a reduced Earth, so we have to oxidize the surface, and then it starts to accumulate. There is also another problem. This is my friend Jerry that have some problem of biodegradation. You can produce by Rubisco enzymatic photosynthesis oxygen. So you take from the oceans CO2 and you combine with water and you produce, for example, sugar. This is the most simple one. You can produce any one of molecules you want, and then as a waste you produce oxygen. So this, they don't like this cyanobacteria, the oxygen, but the humans like very much. We are breathing and doing our metabolism is controlled by the presence of oxygen. But then when the bacteria of my friend Jerry die, is degraded. And you also have organic respiration, and you have aerobic degradation. So you can increase the mass of cyanobacteria producing oxygen, but increasing the mass is changing nothing because all this biomass must be at a certain point degraded. It's die as everything, and dying in an aerobic condition is completely consumed, and you inverse your equation and you go back. If you calculate the net flux of what is produced and what is lost in 50 years time scale, you have no oxygen in the atmosphere. So having oxygen in the atmosphere means that we have an imbalance between the source of oxygen and the sink of oxygen. There are a lot. I will just speak about two. Two models are true, are not, I don't know. As I said, every week we have mostly a paper on oxygenation. So for me, the oxygenation is the most beautiful example of Earth system science, because for me, all the reservoirs of the Earth interact. The geosphere, the biosphere, the atmosphere, to arrive to find this magic recipe to make oxygen accumulate. And still, we are trying to understand what is the complete recipe. So if you try partial recipe, you waste your cake because it will not work. So today, we know how to do to produce oxygen and to have less oxygen lost, because today part of the biomass is preserved in sediments. So, and you have anaerobic decomposition. If you look at these two equations, this is the classic equation of oxygenic photosynthesis, and this equation, anaerobic decomposition, you buried your organism, your biomass in the sediments, so you separate from the atmosphere. And when you do the balance of this equation, in the net reaction, you have, where is here, oxygen that is preserved. So you have an excess of oxygen. Today is very small. Less than 1% of the world biomass is preserved in sediments. We have the proof as geologists. Petroleum is formed this way. The first trace of what the people think it was petroleum hydrocarbon has been contested, has been debated. It was, you will correct me, maybe again Tubiana Formation 2.7. One paper has been contested and completed, but they have trace of what we call hydrocarbons at that period. And so the idea was that we start to have a sufficiently mass of sediments at that period to have a part of the biomass separate from the atmosphere, and so create having an imbalance between the source and the sink. Why 2.5, 2.7? I go back to these figures. When we arrive to have most of the continents formed at 2.7 billion years. So some idea is that is this period because we have large continental masses, they are weathered, they produce sediments, and so you have a huge amount of sediments that start to accumulate in marine basin, and so you can preserve more and more biomass, and so you create a more stronger imbalance between production of oxygen and sink of oxygen. Is this true? It's a very simplistic model. We don't know, but it could be a possibility. And so you related geosphere with the atmosphere, with the biomass and the oceans. There was alternative models. I showed the original one was basically, after I had to move to oceans, I have no choice, is volcanism. So there is an old paper of Camp and Byerly in 2007. There are much more recent ones with Nick Hart and other groups that say that, again, related more or less of the appearance of more and more continental crust emerged from the oceans, so landforms, that another big sink of the oxygen is volcanic gas. So as we saw, the volcanic gas is depending from the redox of the mantle. So if your volcanism is emitting reduced species, they will be oxidized by oxygen. For example, if you have methane and not CO2 coming from a volcano, what the methane reacts with the oxygen is burned. And we saw before the curve of methane, you have this drop because just oxygen became abundant, so methane starts to disappear. And so they make a model, they make some calculation based on an empirical formula of Heinrich Holland that you can calculate on the basis of the chemistry of the lavas what it should be the composition of the gas. And until that period, these two guys say that the Archean volcanism, it was dominantly submarine. It's probably not true. There were also volcanoes on the lands, but anyway, submarines. And so this kind of volcanism produced reduced gas. And so the oxygen was burned out by reducing this gas. And then when we have the post-great oxygenation event, it was in the Proterozoic mostly subaerial volcanism on lands, and this produced more oxidized gases like the Copahue volcano here in Patagonia. And so you have oxidized gases, so the oxygen don't need to enter in the equation. And so it can freely accumulate because you eliminate a big sink, that volcanics. This is two very simple models. We can believe or not, but the importance of this model, that is true or not, is just the things I want to point out, that is not only one factor. It's not only biosphere, it's geosphere, it's the atmospheric composition, the oceanic composition. They have some magic mix or forces that work at that period to make accumulate oxygen. It's not only one factor. And still in the books, you see the old story, just as cyanobacteria develop and produce oxygen. No, you need to have an imbalance between source and sink. Let's move to the oceans because Muriel came here only for the oceans. I don't need to present this guy. Everybody knows if you study Greek in the school of philosophy. Okay, so yesterday we saw a very nice presentation about 67P, and you know that hydrogen isotopes are the best fingerprints for water sources in the universe. As I said before, because the D on H is quite, so the ratio between deuterium and hydrogen, so mass 2 and mass 1 hydrogen, is very conservative, especially on the Earth. So the oceans mostly didn't change this composition. The mantle is a little bit different, a little bit lower than the oceans, because in the rocks you have practically no hydrogen. So in this exchange, you can exchange the oxygen, but not the hydrogen. So a few per mil difference, you can say that the oxygen today have the same composition of 4 billion years ago, or something like that. The mantle is a little bit lower, but still in the same value. So if I look at the perspective of a cosmochemist, this bar here and this is probably 100 per mil difference. As a geochemist that work on the Earth, 100 per mil for me is huge. But for a cosmochemist, is nothing, because you see we change order magnitude. This is the protosolar nebula. This is the gaseous planets. Carbonaceous chondrite, Ryugu, Antarctic micrometeorite that is mostly carbonaceous chondrite, so it's like this blue one. I added the astatite chondrite of Loretta. And here you have the comets, Oort cloud comets. The famous Hartley 2, we don't speak about that. I cannot speak because I'm not specialist. It's been contested, the measurement, etc. I don't know what is happening with this comet. And 67P, the Chury comets here. And the proto-Earth, it was something like that. This is global oceans, this is the mantle. And you see that to have water in the oceans, the only parents that you can admit is chondrite. We can discuss what type of chondrites, but it's chondrites, the Oort clouds and the Jupiter family comets have too much deuterium. And yesterday Catherine explained very well, because is come from an old paper that showed that when you are lower than 50 K or something and you produce a cosmic ice grain, this cosmic ice grain are more rich in deuterium, so in the heavier masses. And when these ice grains start to move in a hotter place, like close to a star, like our sun, during evaporation, you have a reaction between the steam and the surface of the grains, and you start to have water condensating with a more light hydrogen. And so you have what we call the heliocentric distribution of D on H. So when you are close to the star, you have more light hydrogen composition, and when a cold place, you have very high deuterium water, like when you produce cosmic ice grain at 10 Kelvin in interstellar medium, you should have a D on H absolute. This is not per mil in 10 minus 2, while the ocean is 153 10 to the minus 6, so 1.5 10 to the minus 4. Okay, and when we look at these different chondrites, so the astatite we think is formed more or less around the orbiter of Mercury or somewhere there. It's close to this value. The same for the class of the carbonaceous chondrite. This is less water contained. This is the most rich in water. It again is encompassing the value of the oceans. The Oort clouds and the Jupiter family have too much deuterium to be the source of the water. Okay, we could mix this with this, but I show in the diagram before that if you mix comets and the solar deuterium, the Earth is not passing the mixing hyperbola. I don't say any more about the source because yesterday I think it was very well presented. But I want, as a geologist, critics and speak a little bit of the Jack Hills zircon. I already speak before. I explained that you don't need really a continental crust to have. Maybe this model with proto-continents looks like oceanic plateau. It was sufficiently hot to have melting pockets producing felsic rocks where this idea zircon stay. This is the famous outcrops. It's in the Jirgal Craton, south of Pilbara. If yesterday you saw the map of Western Australia, you have the Pilbara close to the coast, an enormous yellow area that is the Gilner Craton, also very old. These rocks have only 1.7 billion, 1.8 billion, but inside contain zircon that is what we call detrital zircon. So the original protolite, the original rocks is disappear, but in one of the geological cycle finish inside another magma that produced this rock. But so these are much older than the rocks that is contained. This is John Valley. A lot of geochemists know him, and the Madison University. And this is Simon Wild. This is a field geologist Australian that work on that. So the first things I have to say that when appeared these two papers in 2001 on the Nature, people didn't have memories. We are always know memories. So this is good because I can always reinvent hot water, and especially now they work in geothermal stuff. I'm reinventing hot water because in '83, Wild, I think, St. Pigeon, that he was a specialist on microprobe like John Valley, published already sample coming from this area and showing that the age was 4.2, 4.3. So the people, the scientific community, at least between geologists, know that this rock exists and they were zircon with this age. But everything has been focused around this one, I think. No, it's this one. No, it's this one. The W74-236, where one part of this zircon gave this age of 4.402. So it was the oldest object. Has been never repeated this age, but you have thousands of zircon now. They have age of 4.2, 4.3. So from the geological point of view, we believe there were rocks that contain the zircon at that age. I don't say that it's not true this age, but it is the only one we have. And this has been used by colleagues using a lot of isotopes, hafnium, or measuring titanium, etc., explaining what it was the condition of formation. And one thing that is very important is that with what has been found concerning the oxygen isotopes, so this is the ratio of oxygen 18 or 16, people say the oceans was there at 4.4. I don't know if the ocean was there, but there were this value. So this is the value of the mantle. It's a plus 5.3 per mil. And in this part of 4.4 has been measured a value of 7.4, and also in others zircon of 4.3, 4.2, but I'm not surprised for younger zircon that you have this, because if you go today in zircon is magmatic rocks, for example in granite of Anatex Sea, so that means you take crustal rocks and you go to melting them and creating granites, the delta 18 oxygen will be not plus 7 but will be plus 10 or plus 12, is that to create this anomaly you need that you exchange oxygen with some rocks that is wet. That means that at that time the condition was to have stabilized liquid water on the surface. So expecting that most of the water arrive with things with the late Venier when the planet formed, we could say that at least the volume of the oceans were there. But it doesn't mean that it was 15 degrees. There were palms around and beaches and blue elephants around, because to have a stable water liquid at the surface of the Earth is a question of temperature or pressure. So if you have a Venus-like, even more diluted than Venus with a certain pressure, you can have liquid water with a surface temperature of 100 degrees or more. You have the diagram of water up to the triple point that is 374. You can move from steam to liquid water. You just change all the temperature of the pressure. So at 200 degrees, I could be still a liquid if the pressure atmosphere is, I don't remember how much bar, because as a bad geologist, I forget always all these diagram of physics and chemistry, okay? So probably the liquid there was some hydrous rocks. People say they were hydrous supracrustal rocks. Supracrustal rocks means rocks that was at the surface and became sediments, wet, and then bring it down to high temperature to melt and form some kind of granites, or granitoids, I will say. I don't like the granites I like to use for modern granites. And so that is the meanings of this value. This is the meanings of this zircon. There were liquid water and there were wet rocks. Then you have some hydrate mantles, so do you really need at the surface? But this is the means of this zircon, okay? So I move the last 3 or 4 slides. For the people that are doing the life kitchen here, so biologists, you want to know there were liquid water. That is very important, because the 99.9% of biological reaction in your laboratory you do in presence of water, so you need water as a solvent. There are people that are now using other material, but the most simple is to have a liquid water. And then they want to know, it was hot, it was salty, it was acid, it was, I don't know. So it was containing oxygen, etc., etc. So it was hot, following, this is the same diagram that they present. And as I said in the title, it was hot oceans. Who cares? Extremophile like thermophilic cyanobacteria, it can live between 60 and 80 degrees. So even if the ocean was 60 or 50 degrees at that time, this kind of extremophile can live. If it's not extremophile, we correct me, because I forget a lot of things. Before I know all the metabolic pathway, because I working on that, and now I forget everything. Sorry for that. So again, the conditions are harsh, but there are organisms that can live at that temperature. They can live at that temperature with maybe still high pressure of CO2 or this mixing of gases, because we know we have organisms that live at high pressure at the bottom of the ocean, so they like to live at high pressure. There are the other they like to live at low pressure in the atmosphere. There are prokaryotes that live in the Antarctica, in the desert, in all extreme conditions. This reason we call it extremophile. So what he was acidic, basic, etc. Today is basic, is 8.2. Even if this number is changing, you know, the famous acidification of the oceans caused by the CO2. This is a very old diagram that I calculate. I use this equation to calculate if I am the oceans in equilibrium with an atmosphere with only CO2. This is not a Jim casting curve, it's another paper of some Japanese. So this is plotted the CO2 decrease with time, and this is what will be the increase of pH using this equilibrium equation. If I imagine that all depend just by the equilibrium of a gas with the oceans, but you know that you have the precipitation and carbonates and dissolution that control this equilibrium now. In the past, there were no carbonates, and there is a very nice paper of Francis Albareda, Archaeoceanography, the title, that explained that maybe iron and banded iron formation that were played, what is playing now, the carbonates to control the alkalinity, okay, of the oceans. And so, but we move from pH around 5.5, 6, 4 billion years, and we finish today around 8, so just playing with the equilibrium between, for example, CO2 and the oceans. The model of Francis have values around between 6 and neutral 7 for the Archean, 3.5. So again, we are also, if it's basic model, he used a model mixing CO2 and methane. Again, it was acidic, but again, it's not extreme. It's not. I put my naked feet in the Kaviawe Lake, that is the biggest acid lake in the world, close to the Kopawe volcano that I showed before. It's not the most acid. The most acid is in the Merapi. The pH is negative. Don't put anything inside there. You form a bowl, empty bowl of sulfide. It is so acidic. But I put a feet, and my feet is still there. So 5 is not dramatic for organisms, so, or 5.5. So again, you can have a streamophile that live well there. Salinity. Mother sources do not work at the Archean because you have two sources. The mantle that give halogens with elemental isotope, elemental composition chondritic. I disagree a little bit for the, it was chondritic composition, probably fractionated. So, and they came from the mantle, so halogen has been bring by chondrites and rejecting the oceans through this chimney. By volcanism, because hydrothermalism, because halogens like water, don't like stay in the rocks, so they concentrate in the oceans. But today, continent alteration runoff give you the majority of cation anions and control the flux of alkalinity with the precipitation of carbonates, etc. But at 4 billion years, it was at 3.5, Francis calculated 20% of the surface of the planet covered by continents. At 4, it was probably less. So you have an imbalance between two sources because the Earth was an ocean planet. It was not a planet like we know today. So we had to think about what it was really the salinity. So as a geologist, so some people say that the salinity was like today. In terms of major chemistry, salinity is a 90% NaCl, halide. So, and there is model that follow a little bit reaction that we have on the Venus, where you make reacting at least on this planet oceans that the Earth, a Venus-like atmosphere reacting with sodium-rich basalt is containing some minerals we call plagioclase, a lot of sodium. And amphibole that contain chlorine, and so you produce a brine that is grossly similar to modern seawater. And you can start to produce this even at very high temperature at 300 bar of pressure atmosphere. This is a model of sleep in 2001. So probably you have some halide-like chemistry on the oceans that time. And as a geologist, we went to search the lost salinity, like a title of Indiana Jones film. Inside this fluid inclusion, the rocks contain fluid inclusion. When I was a student, I think the fluid inclusion cannot be preserved for a long time. This is a very nice fluid inclusion because you have liquids a gas bubble and an halide crystal inside. And there is a very old paper in Scientific American, Edwin Roeder, that is the father of the fluid inclusion. He was a Virginia Tech professor, and he is the most famous expert in the world. He died a few years ago on fluid inclusion. And in this paper said the inclusion, so when a mineral crystallizes out of a brine, some of the brine is trapped in small fluid inclusion. Does the inclusion provide sample of solution? They may be more than a billion years old. And so people went to search in all terrains, claimed to find the primary fluid inclusion, and they measured the chemistry of the fluids and arrived at the conclusion that the salinity at that time, this is rocks of 3.5, it was probably 1.2, 1.5 to 2 times the salinity of today. So in the Red Sea or other places we have, again, extremophile, they'll survive much more salinity. And the salinity you see was very similar to the present day, except some exception. They were, the blue is the Archean salinity, the present one. They were less sulfate and more because the sulfate was in reduced species and not as sulfate in the oceans. We have a variation in the iodine and bromine. Somebody said for iodine, because iodine today is used as metabolite with some prokaryote. So at the time there was no sufficient biomass to absorb all the iodine. So you have an excess of iodine in the Archean. And then you have more calcium and strontium in solution, because today calcium and strontium with magnesium is in the carbonates, precipitated. At the time you have no carbonated platform. And so the chemistry was, with a small difference, very close. So I arrived to the last two. The last one is a philosophical. It's what I learned from astrobiology and what advice I can give you. I never give advice to the student. And then I start to make like my father. The student don't work so much. The student do this, etc. So I discovered I became old. I'm 5 years from my retirement. I start to give advice to the student. You can keep that, or you can throw away, is your business. So I go back to the initial one. I like this picture. Is one of the 1,000 picture, the artist picture, but it's nice because the moon was closer, so the tidal was more important. The sky should be red if it was a lot of CO2, because when it is CO2 dominant, is the red light that is dominant, is not the blue one. So Papa, why is red the sky? Probably say the Archean kids to his Archean father. And there were no oceans, there were stromatolites. So this was probably, I don't know if the other geologists in the room agree, maybe 2.5 or 2.7 or something like that. There is no comatite around, so I cannot say, or TTG, okay? And so the last one, the lesson from my journey into astrobiology. It was exciting science. I think still is exciting science, and truly transdisciplinary. When I started with Muriel, we were in a room with pure chemists, pure geologists, pure astrophysicists, each one looking the other bad, and each one believing that the other know the truth. And so it was a very famous chemist that was the president of the Academy of Science, that at the first Congress I came, at the first school, somebody speak about the geological condition, and the guy said, but where are the geologists? Explain me what is happening. The geologist was Hervé Martin and myself that disappeared under the chair because he was the president of Academy of Science. For us geologists, a president of Academy of Science is a genius that know everything. So you know probably everything about chemistry, but he was not a geologist. So we learned that each one know a piece of this puzzle and add his information to try to resolve this puzzle. I think the puzzle is not yet resolved. He helped a lot to improve instrumentation. When I was a student, I didn't have an instrument to study microfossil. I make a paper on microfossils. The famous apex chart at 3.5 billion years, contesting the origin of that, is my only Nature paper because, again, I make fancy things, so I publish on Nature. And now we can see the extremely small or the extremely far for you astronomers that we could not do 30 years ago, 40 years ago. I think astrobiology helped a lot. We have a different view of our planets. We have a brilliant student. Everybody is brilliant here and with a lot of idea. And I was surprised when you make your 90 seconds because when I was student, was geologists trying to do astrobiology. Now I have geologists that move to astrophysics or to chemistry or biology. So in your academic journey, you are moving to a discipline that is more and more complicated. But for a geologist, it probably is not happening for a science. Speculation was always behind the corner, and still is, for two reasons. I don't know, for us geologists, because we do science but also poetry. So sometimes, as I said, there are people with a mineral that try to convince us that we have blue elephant in the Archean. And sometimes because you will have fantastic results that you will publish in Nature or Science, this big journal. And once one editor of the Nature came in McGill University, make a presentation, he make a circle, he say, this is the circle of the no science. We publish outside. And so in my mind, I think, like the cold fusion. But I didn't say the high voice to avoid accident with this editor. But you are pushed to go a little bit far from your data. It's more easy maybe in geology than in astrophysics, because you have like gravitational physics that is imposed, or Einstein physics that you cannot break because it seems are valid. Everybody agree on that. And so I was tired a little bit of this speculation. For this reason, I left the astrobiological field, even if there are people are convincing me to go back. So I have two projects: understanding planetary nitrogen, what is the real source, working on very old rocks with the Japanese, and with Dijon and McGill working on the oxygenation and the eukaryotic life. Will be marginal my work, but I'm putting back on this field. You just be careful to keep your feet on the ground, because it is easy to move on that. And this make me tired at a certain point. We have the same discussion with Jean-François. And so I moved to do other things, but as you saw in some of my papers, like the halogens, I start to speaking about giant moons and planets. So always I have an eyes of what it could be some global consequence that could be useful for astrobiology. Thank you for your attention. If you have questions.